Good morning, everyone. Hope all is well. Hope everyone's doing all right. All right. So, we're getting into probability today, I believe. Okay. So, hope everybody's doing great. Everybody's all right. Yep. Chapter 5. All right. So, let's go ahead and get rolling. Probability rules. I'll let you copy that. I need to get my charger real quick. So, give me 1 second, but you guys can go ahead and get started copying. I'll be right back. All right, I'm back. Just had to make sure my charger was in place because sometimes this thing, the battery get low and I'm not paying attention. It will not let me know. It'll just shut me down. So didn't want to put us in that type of situation. So probability rules 5.1. Probability is just a measure of the likelihood of a random phenomenon or chance behavior occurring. All right, then we have the law of large numbers as number of repetitions of probability experiment. Don't know what you mean by definition with a question mark. It says as the number of repetitions of probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. So the more times you perform an experiment, the more you get, the closer you get to the actual probability. Yeah. So like I said, like this. All right. All right, now scroll up. All right, so that takes us into an experiment. An experiment is just any process with uncertain results that can be repeated. So a light example of an experiment is just flipping a coin. Holding on to the black. Yeah, we'll get to that part. We'll get to that. Mhm. The collection of all possible outcomes of an experiment is your sample space. So an example, when it comes to flipping the coin, all possible outcomes, heads and tails. And that's denoted by S. And then your event is just any collection of outcomes in from the sample space. So if like you want to know the probability of landing tails, tails would be your event. And that's denoted by any capital letter. Normally you wouldn't use S because remember S is reserved for sample space, but any other letter you can use to represent your event. All right. Let me know if I go up too far. Okay. So rules of probabilities. First one, probability of event E, P of E. So P parentheses E, just the probability of that event E occurring is always going to be in between 0 and 1. And that is inclusive. So it could be equal to 1, it could be equal to 0. If it's equal to 0, then there's 0 chance of it happening. If it's equal to 1, it's 100% chance of it happening. But your probability is always going to be within 0 and 1 inclusive. And then the sum of all the probabilities and the outcomes in your sample space, well, when you add them up, that will equal up to 1. So of course, when we get an example, put numbers on it, stuff will make more sense. All right, scrolling up. So here's just a statement saying that the probability model must satisfy both rules 1 and 2, not just one or the other. Right. So give you a chance to copy this down, but we want to verify that this is a probability model. So, you can think about let's see what has, well, M&M's has brown, yellow, red, blue, orange, and green. So think about a bag of M&M's. If you have the probability already calculated for you, 13% chance of getting brown, 14 getting yellow, 13 red, 24 blue, 20 orange, and 16 green. You want to verify. All right, somebody else to scroll up there and get number 2. All right, can we scroll up now? All right. So that's the rest of the chart. All right, so let's look at it. Rule 1 and rule 2. Rule 1 is that your probabilities all have to be in between 0 and 1. Rule 2 is that when I add up all these probabilities, they will equal to 1. Cannot be less than 1, cannot be more than 1, has to equal 1. And so rule 1 is just observation. You look at all your probabilities and we see that each one of them, each probability is between 0 and 1. And then rule 2, when you add them all up, notice we end up equaling to 1. So since the model satisfies rules 1 and 2, it is a probability model. So that's all they meant by verifying that's a probability model. Make sure it fits within the scope or the realm of 1 and 2, rules 1 and 2, not one or the other. All right, scrolling up. Are we okay? All right, so an event is impossible if the probability is 0. An event is a certainty if the probability is 1. So notice 0% chance of something happening. 1 is 100% chance of something happening. The closer probability is to 1, the more likely the event will occur. The closer the probability is to 0, the less likely the event will occur. An unusual event is an event that has a low probability of occurring. Anybody holding on to the certainty? And typically, an event with probability less than 0.05 or 5% is considered unusual. So it's not set in stone, but that's what we will use throughout this book. Is that 5%, something less than 5% chance is considered unusual? You know, if you were doing your own statistical analysis, you always could set it a little higher or lower, whatever, but that's what we'll be using. 5% is the marker. Anybody still using that unusual statement? Okay. So let's look at calculating probabilities. So the empirical approach, I think I just said approach, but the empirical approach, probability of event E occurring will be the frequency of E over the number of trials of the experiment. All right, right done with the red. All right, so we have an insurance agent currently insures 182 teenage drivers. Last year, 24 of them had to file a claim. Based on these results, what is the probability that a teenager will file a claim in a given year? All right. So to do this or calculate it empirically, take the frequency of E or your event, place it over the number of trials of the experiment. So in this case, we have 24 teenagers to file a claim. We have 182 teenagers altogether. So you place that 24 over 182, and that gives us 0.132. So before we get to that purple statement, any questions on what we did there? The larger number will always be the bottom number. So remember, your probability can never be over one, larger than one. So if you were to do 182 divided by 24, that will give you something way larger than one. So that's how that works. All right, so now when it comes to your answer, MATLAB is going to present the answer to you, or to present the answer or option of an answer to you one of two ways. It may ask you for the actual numerical answer. If that's the case, then you can just put in 0.132, or it may ask you for, or they may give you a sentence, may give you like 4 sentences to choose from. So let's see. Yep. So it may give you 4 sentences to choose from. So if it says something like this, if you look at this statement, it says, so for every 100 teenage drivers, we expect about 13 to have to file a claim. So in other words, what they did was, and I wrote it in this blue right here. If you take the 100, multiply it to this number, that's where this number would come from. So 100 times 13.2, I mean 0.132 is 13.2, which is about 13. So let's say if they said, so for every 1,000 teenage drivers, then you would take 1,000, multiply it to this, and that number over there should be 132 to have to file a claim. So whatever this number is right here, they're expecting you to multiply it to this probability, and that number should match up with this number right here. So what they'll do is, like I said, if they have something like this, they'll give you like 4 statements to choose from, and you will have to make sure those numbers match up. Once again, you take the number, the 100, multiply it to your probability number, and then that will give you this number down here. All right. So is everybody okay with that before we go to the next thing? Not necessarily copying, I'm talking about just the concept of what they're doing. So once again, they'll give you a number. So for every, like I said, if they say 1,000, you would take that 1,000 and multiply it to this number right here. And that should be this number right here. So if it was 1,000, they would say about 132 have to file a claim. All right. Everybody okay? Everybody done with that green? Okay, so the next method, classical method, very similar to the empirical method. Probability of event E. So we have the number of outcomes in E over the number of outcomes in the sample space. And here's the notation for that. N of E over N of S. N of E represents the number of outcomes in E. N of S, the number of outcomes in the sample space. All right, so let's try it out. We can use the flipping the coin example. The probability of landing tails. All right. So first thing you want to do is establish your sample space. That's always the first move to make when dealing with probability. Figure out how many outcomes you have altogether, total from your event. So we already know when it comes to flipping a coin, the only choices we have will be heads and tails. So we have 2 outcomes, 2 possible outcomes. So the number of our S, number or N of S, number of all outcomes is 2. Then you establish your event. How many outcomes do you have in your event? In this case, it's just tails. It's only one way to get tails. So that's the number of our event. So once you do that, find the probability, place the number of the event over the number of your sample space. And that's 50% chance, 1/2. So I know most of you already know that, but that's how you do the process. That's the mathematical way or statistical way of finding it out. But you always stick to this process. Once again, find your sample space, establish the total number of outcomes in your sample space, and establish the total number of outcomes in your event. And then you place the number of outcomes in your event over the number of outcomes in your sample space. All right, can we scroll up? Do a real example. Okay, we have a single dice roll. What is the probability of landing a number greater than 2? Are we done with the blue? Last problem. Okay, so let's walk through what's happening here. So a single dice roll, if you don't haven't dealt with dice before, whether it be board games and all the stuff, Monopoly, here are your outcomes right here. 6 outcomes on a regular single die. You have your pips, 1, 2, 3, 4, 5, and 6. So that's this right here, just me trying to show that or giving an image on that. So our sample space is 1 through 6. And so the number of outcomes is 6. Now, what I wanted to make sure we understand here is that this 6 and this 6 does not have anything to do with each other. Like the number of outcomes is 6. So if this was 1, 2, 3, 4, 5 triangle, the number of outcomes would still be 6. If this was 1, 2, 3, 4, 5, 10, the number of outcomes will still be 6. So make sure we're not confusing that, this 6 right here has something to do with this 6 right here. Then they don't have to be. And so this is just the counting right here is just the counting of outcomes that you have. Here's just listing the outcomes that we do have. All right. And then we want to know the probability of getting a number greater than 2. So all the numbers that are greater than 2, 3, 4, 5, 6, and the 4 numbers that are greater than 2. So that's the number of those outcomes. So questions before we look to finish all the problem. All right. So now we place the 4 over the 6 and then simplify as much as possible. 4 is 2 times 2, 6 is 2 times 3. Those 2's can cancel. And our probability would be 2 over 3. All right, scrolling up. Okay, so this time we have a pair of dice is rolled. We want to compute the probability of rolling 7. Then B, compute the probability of rolling snake eyes, which is rolling a 2. All right. So once again, we want to establish our sample space first. So we got to be careful here. When you talk about establishing your sample space, you want to know all of the combinations that are created by rolling 2 dice. So, when die 1 is 1, die 2 is 1. When die 1 is 1, die 2 is 2. Die 1 is 1, die 2 is 3, and all of those combinations. And you're talking about 2, 1, 2, 2, 2, 3. All those combinations, 3, 1, 3, 2, 3, 2, and so on. So we can use the fundamental counting principle instead of listing out all of those combinations and possibly missing one. Fundamental counting principle says that if I have 1 die and I know all the possible outcomes, which is 6, then my other die is 6. And all I can do is choose 1 out of each. I can just multiply those together, and that'll give me 36 possible outcomes. So if MATLAB give you something weird and they say 1 die has 8 faces and the other die has 6, then all I would do is do 6 times 8, and then that would be 48. I don't think they will, but I'm just throwing it out there. If 1 die had 10 faces and the other die had 7, 7 times 10 is 70 total possible combinations. So you just multiply those numbers together. All right, so that's why we're here with 36 number of possible outcomes in our sample space. Now, if you're talking about rolling a 7, we can list out all of the possible ways of rolling a 7. So here you talk about die 1 being 1, die 2 being 6, then 2, 5, and 3, 4. Now, die 1 being 3 and die 2 being 4 is different than die 1 being 4 and die 2 being 3. So you have to give an account for the opposite. So that's why we have 5, 2, and 6, 1 as well. So we have 6 different ways that we could roll a 7. So the number of my event will be 6. So once you establish both of those numbers, then you go ahead and write your probability. That's 6 over 36, which is just 1/6. Any questions? Any questions? All right, can we go to the next one? So B, rolling snake eyes. Want to know the probability of rolling snake eyes, which once again is 2. So we already know the sample space. We haven't changed the problem. Oh, somebody said something in the chat. Yep. So we already know the sample space. We haven't changed the problem. Sample space still 36, and we still have 2 dice. And then the probability of your event is just 1. There's only one way of getting a 2. That's when die 1 is 1 and die 2 is 1. 1 plus 1 is 2. There's no other way to get that. So that'll just be 1 over 36.
I have a question.
Yes.
Are our answers on MATLAB going to be like fractions or decimals, or do you know?
It could be either or. Yep. So these more than likely will be fractions, but the ones we were dealing with before, that'll probably be in decimal. And so, yeah, they're going to vary between, those both of them. So you just got to watch those directions and stuff. Good question. Good question. All right. Everybody good? Can we scroll up? All right, first part of this problem. Suppose a survey asked 500 families with 3 children to disclose the gender of the children and found that 180 families had 2 boys and 1 girl. You got an A and B to this. Yep. Is everybody done with the probability? Let's scroll up. All right. So estimate the probability of having 2 boys and 1 girl using the empirical method. And we'll get to B in a second. I want to give you guys a chance to write. All right. Then compute the probability of 2 boys, 1 girl using the classical method. All right. So A, we wanted to estimate the probability of having 2 boys and 1 girl using the empirical method. So you go back to your problem, we have 180 families. They have 2 boys and 1 girl, but totally we have 500 families that were surveyed. So we just do the 180 over 500, and that's 0.36. Once again, MATLAB will let you know if they want decimal or fraction or whatever the case may be. I know this problem, putting it out the book, they left it at 0.36. So any questions on A? All right, so B, the classical method. So what we're gonna do is perform a tree in order to figure out theoretically how many total outcomes can occur. So we talk about firstborn, secondborn, thirdborn. When it comes to firstborn, there are 2 options. First, we start off with option of having a boy first. Then from there, it's possibility of having boy or girl in the second shot. And then after the second shot, possibility of having boy or girl, and then possibility of having boy or girl. So we list out all the different possibilities of having 3 children, starting off with the boy, then having a second boy, but then and then going boy, girl. So in that first option, we have boy, 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 and we have boy, boy, girl. Then we do boy, girl, boy, boy, girl, girl. And then the next one, we start off with what happens if you have a girl first? How many options do you have? So we're just talking about all in general, how many total possible outcomes can occur. So from having a girl first, it's possible to have a boy or girl. Then from having a boy or girl, you have boy or girl here, and then boy or girl here. So in general, we have 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. That's your sample space. So that's what I have right here, 8 possible outcomes. So generically, we have 8 possible outcomes if you're gonna have 3 children. All right. Now our event is 2 boys, 1 girl, not necessarily in any specific order. So then we will look at our 8 outcomes and see where do we have 2 boys and 1 girl. So here we have boy, boy, girl. So that's one. Then boy, girl, boy. That's the second one. And then girl, boy, boy. That's the third one. So we have 3 different outcomes that will create 2 boys and 1 girl. So once you have both of those, you place the 3 over the 8, and that would be 0.375. All right, any questions on that? All right, anybody still copy? Can I scroll up? All right. Okay, so let's start 5-2. I'm not going to try to finish, but at least started. Got a little time. So we have the addition rule and complements. So we start off talking about disjoint events. 2 events are disjoint if they have no outcomes in common. It's also called mutually exclusive events. All right. So the addition rule for mutually exclusive events or disjoint events, both of those, like I said, mean the same thing. If E and F are disjoint, then we can just add the probability of E plus the probability of F in order to find the probability of E or F occurring. Anybody still holding on to the purple? You okay? Everybody okay? Okay. So deck of cards. All right. So it says still copying the purple. All right. So we're looking at a deck of cards. So just in case you're not familiar with how cards go, just want to make sure we're clear. So we have a standard 52 card deck. That's what they'll always mention. That means that there are no jokers. So in your standard 52 card deck, there are 4 suits: spades, clubs, diamonds, and hearts. Your black suits, in other words, black cards, are spades and clubs. Your red suits are red cards, diamonds, and hearts. There are 13 cards in each suit. 13 times 4 gives you 52. And so we have 3 face cards and 10 regular cards. Okay, I'll scroll up in a second to finish it off. Somebody was copying. All right, so your face cards, king, queen, and jack, and your regular cards are considered your ace, and then 2 through 10. So your ace is not a face. Ace is not a face card. All right, can we scroll up? Yep. Mm-hmm. So suppose we have a single card that's selected from a standard 52 card deck. We want to compute the probability of drawing a king, then compute the probability of drawing a king, queen, or jack. All right. So just like before, when we talked about trying to find your probability, you want to establish the number of your um, sample space first. So first thing I did here for A, total number of possibilities or total number of cards, 52. Remember, we have a 52 card deck. Then the total number of kings. We have 4 kings in each deck because we have 1 for each suit. Remember the first, we just want to know what's the probability of drawing a king. So probability of drawing a king would be P 4 over 52, excuse me, which would simplify to 1 over 13. All right. So going to B, one, compute the probability of drawing a king, queen, or jack. So when we look at all three of these events, drawing a king, drawing a queen, drawing a jack, these events are mutually exclusive because they do not have any cards in common. You cannot be a king and a queen, cannot be a queen and a jack. They have no cards in common. So of course we'll get to an example where we will have that, but that's not this case right now. So since they're all mutually exclusive events, and we can find the probability of each one of them individually. Is everybody done with A? All right. So it just so happened that all of their probabilities are all the same because we're dealing with cards and they're the same amount of kings, same amount of queens, and the same amount of jacks in these cards. But I went through the process anyway because if you were doing it on your own and you didn't have this scenario, you would have to go through each one of the probabilities individually and establish where they are. So the first thing you would do is establish the sample space. In all three cases, it will be 52. Then you establish how many cards or how many outcomes do we have in each one of the events individually. And in this case, all four of them will be 4 because there are 4 kings in the deck, 4 queens in the deck, and 4 jacks in the deck. Okay. Once you have both of those pieces, you place the 4 over the 52 and then add them together because they're mutually exclusive. So everybody done with the red? So 4 over 52 plus 4 over 52 plus 4 over 52 will be 12 over 52. And you can reduce that by 4, which will give you 3 over 13 or 3 out of 13 chance. All right, any questions? All right. Single dice tossed. Let's see how much more is left out of 10-2. All right. So we can do this last one for today. Is everybody done with that king, queen, jack? All right. Single dice tossed. Find the probability of rolling a number less than 3 or greater than 3. So we want a probability of rolling a number less than 3 or greater than 3. All right. So looking at what we have here. Let me do it. We have 2 different events. We have less than 3 and greater than 3. They are mutually exclusive because it's impossible to be less than 3 and greater than 3. They don't have anything in common or any numbers in common. So we go back to our die, and that gives us 6 outcomes in our sample space, 1 through 6. Now, being less than 3, the numbers that are less than 3 is 1 and 2. So there's 2 outcomes in that fits that description. So there's a 2 out of 6 chance of rolling a number less than 3. Are you okay with that? Got it ready to go to the greater than? So then we have greater than 3. That's 4, 5, and 6. 3 outcomes fit that description. So it's 3 over 6. So then from there, once you have both of those events, the probability of both of those events, you can go ahead and add them together. You have the probability of having a number less than 3, probability of having a number greater than 3. That's 2 over 6 plus 3 over 6. And that'll be 5 over 6 as your probability. Questions, questions, questions. Make sure you're okay. All right. So this is a good place to stop. Let's see. Yep, going to the general addition rule. Good place to stop. Somebody said something in the chat. Yep, it's called the addition rule. All right. So next class, we'll get into the general addition rule when we don't have mutually exclusive events. There's one extra piece we have to look at or consider when we actually go to do our probabilities, if they have something in common. And we'll go from there. So we'll pick up right here on next class. Any questions before we close out? All right, somebody said they had a random question. Okay, how do we know what the grade is in the course? Generally, MATLAB has a grade up there and let you know where you stand as far as MATLAB is concerned. Only time that could be deceiving is if you haven't done everything you're supposed to do. In other words, with MATLAB, if you have not attempted an assignment, it has not counted it against you. So if you have not, let's say you haven't done test 1. Well, if you haven't done test 1 in my book, that's a 0. But if you never do test 1, if you never go in there and make an attempt, it won't count it against you unless I put a due date up there and then it says, something like that. Then I make sure and ensure that it tells you. But right now, since our due dates are all the way out and to the end of the semester, you wouldn't know unless you've done everything you're supposed to do. And if you've done everything you're supposed to do, then the grade in MATLAB is actually lower than my grade, because remember I said 75 or better would be an A for your homework. So I can always give you a general assessment as to what I see if you were to email me, if you just, if you want to know, but it's hard for me to give you a true assessment. Let's say, like I said, if you haven't done test 1 or something like that, if you haven't done the major assignments, all I can do is say, well, you look good up to this point, but you still haven't done such and such. So really, if you want me to do it, I do need some real, work to be done so that I can actually assess you on. So yeah. It's not, all right, let me say this about grades real quick. It's not misleading. It's just that the grade in math lab can't count anything against you that you haven't submitted. So that's why I say it's just giving you where you stand up to that point. But if you really want me to give an honest assessment, if you haven't done something, I'm going to count that as a 0 because that's what I would do in your final grading. Yep. Ms. Brooke?
Yeah.
Mhm.
I wanted to just ask a quick question.
Mhm.
I see that we have 2 attempts for our test, and I did
Mhm.
really good on one of my tests, but I kind of want to see if I can get a 100. If I do bad or something happens, like, does it keep the best grade, or is it to keep the one you do like the second time around?
Great question. Just keeps the best grade.
Okay, just making
Yeah.
sure.
Yeah, it's no problem. I don't even look at the attempts and see what the lowest was and anything like that. And no, whatever the best grade is, that's what I'll take.
Okay, thank
Mhm.
you.
Yep, no problem. And Math Lab should recognize just the best grade. Even though it'll show you what you've done if you were to go in and click and stuff, but it should just recognize the best grade. Yeah.
Okay.
Mhm. Somebody, Miss Destiny, was that a mistake or is that a question? I see 2s and I don't know what that is. I think maybe somebody hit it, they fat fingers and things. Let me know if that's a legit question or not. If you guys are good, I'm good. No one else have any questions. And I'll see you next class. Have a great weekend. Be safe. And we'll pick up right here. Looking at the general addition rule in 5.2. All right.
Thank you.
Thank you. Have a good one.
You too.
Take care.